problem. So we have over here, we have a box on a wall. And what we want to do is we want to take a look at if we push it really hard, it's going to slide up the wall. And if we don't push it hard enough, then it's going to slide down the wall. Thus, anything between those two forces and the box will stay stationary. And to solve questions like this, we have to look at two separate cases because there's going to be two separate free body diagrams, which will lead to two separate equations. Now, a lot of the forces stay the same, but if the box were to move or accelerate up the wall, then friction is going to be pointing down the wall, opposing that motion, right? Friction is going to be the grinding of the two surfaces, meaning the box and the wall. And if you didn't push hard enough, in theory, the box could slide down the wall and then friction would have to point up. So let's look at this. I gave you give you a mass, I give you an angle, and I give you the coefficient of friction, and then you're pushing up on this box. So case number one, let's assume that the box accelerates up. And so then we get this free body diagram. We're pushing up and right. The normal force is always going to point perpendicular to the surface. The surface is the wall, and so it is then going to point straight left. Friction is going to be down, opposing the motion, and gravity, of course, is down. So x hat and y hat are the right forces minus the left forces, and that's equal to 0. And then the up forces minus the down forces equal to 0. And again, I'm setting even the vertical force equal to 0 because I'm solving for that maximum. Anything more than this, and then it actually will accelerate. Okay, so we do our classic thing where we use this equation here to find that the normal force is equal to Fa cosine theta, and then we replace the force of friction by mu times the normal force, and so we get this equation. Fa sine theta minus mu times the normal force, but the normal force is Fa cosine theta minus mg equal to 0, and we just solve for Fa, and so we get this equation for Fa, and when I plug in the numbers, I get 63.97 newtons. Okay, so that tells me that if I push exactly at 63.97, the box is just barely going to be stationary, and if I push anything harder than that, the box will accelerate up. Think about it. Look at this equation again here. This Fa makes it 0. So if I push anything harder than 63.97, this term here will be bigger than friction and gravity, and it will then cause the box to accelerate upwards. Okay, so this is the maximum force that I can push with such that it doesn't move. If I want to accelerate it up the wall, I'd have to push harder than that. And if you actually had an acceleration you wanted to achieve, well, then you just put it in here. You would just put in an MA there that you wanted to do, and then you could get some force. But again, I'm telling you that if you had an acceleration of, let's say, if you wanted to get 2 or 3 or 4, it'd have to be bigger than the 63.97. Okay, so now let's look at case number 2. Let's assume that we're not pushing even hard enough to keep the box stationary, and then it's actually going to, slide down the wall. So this is case 2. Normal force is still left. Now friction is up. We're still pushing up and right, and then gravity is down. So we get the same idea. Fa cosine theta minus n equals 0 for horizontal. And then vertically, let's assume that it's on the verge of accelerating downward. So we make the down force positive. Mg minus Fa sine theta minus friction. Again, Fa sine theta and friction are both up. Mg is down, and we solve and we get this setup where it says that this minimum force that we'd have to push with, and putting in the numbers, we get 50.7. Again, that's the minimum force you'd have to push with to maintain the box just chilling on the wall. Anything less than that, and then look, if you make Fa, and look at this equation, if you make Fa any smaller than 50.7, then these two guys are going to be smaller than mg, and the box will accelerate down the wall. Thus, these min and max problems, eventually you end up getting some range, and it says this. Look at this. The range of forces to remain stationary. If you push any harder than the 63.97, it will go up. If you push any less than 50.7, it will accelerate down the ramp. Anything in between there, the box will remain stationary. Okay? So anytime you're looking for these mins and maxes, you have to look at two cases, because in case number 1, it might go up, and in case number 2, it might go down. Okay?